Okay, so what we had just looked at was, given a vector function r, let's find v, right? Let's take a derivative. What about questions that go backwards? So let's say you have a moving particle that starts at the location 314 and has initial velocity 159. So at time zero, this bug is moving instantaneously in the direction of 159 with its speed being whatever the magnitude of that vector is. And let's say the acceleration is given by this vector function. So a arrow of t is 2 comma 6t comma 5t. So let's find the velocity vector function and the position vector function. So we have acceleration, right, which is the result of differentiating velocity. We have to go backwards. So guess what? It's integration time, right? So here we go. So v prime is a, so to get v itself, we need to anti-differentiate a. All right, so let's do that. Ooh, I've left off a dt. Please forgive that. Okay, so slide making is, well, all right. Let's just get to it. So we've got our anti-different, so this is an indefinite integral. We need to anti-differentiate 2 and 6t and 5t. Those are all not so bad. Keep in mind, though, when anti-differentiating, there's going to be this plus some vector, c, right? Some constant vector. Now, what vector is it? This is where knowing that at time t equals 0, the v vector the function is supposed to return, it's supposed to output the vector 159 is going to be helpful. So let's go ahead and plug in t equals 0 here and set it equal to this vector 159 there. So if we set t is equal to 0, in the two terms that we get, actually everything in the first part drops out, and we're just left with, oh, that shouldn't be a plus sign. That should be a comma. I think you're fine with that. And then plus the c vector. So we set that equal, and then we'll see that c here itself has to be 159, right? Because the first vector is just the all zero vector, or the zero vector, I guess we call it. So here's the velocity vector, replacing c with what we just found to be 159. And of course, this could be written differently just by doing the component-wise addition. Now that this is the velocity vector, right? It's the velocity vector that takes into account that the velocity at time 0 should be 159. We can anti-differentiate this to get the position function. So we'll do anti-differentiation again, one component at a time, plus we've already used c, that's why this is called d. And then keeping in mind that the initial position was 314, plug in t equals 0, and this 0, 0, 0 vector plus, we don't know what the d vector is yet, is going to have to be set equal to the 314 vector. This will tell us that the d vector is 314. So here's a way to write the position function, and perhaps it's a little simpler to do the to do the vector addition here. Quick, I think very mundane interactive question, but why do we need another constant vector? Okay, a moving particle has initial position 2, 3, 4. If its velocity is given by 1 over 1 plus t squared, and then 1 over root 1 minus t squared, and sine of t as the three components, let's find the position function. So here we are doing the same thing that we just did, but just one fewer stage, right? Because the previous one, we started with acceleration and had to go all the way back to position. So that was two sets of anti-differentiations. Here we're only going to do this once. Just a friendly reminder here that the functions picked were hopefully nice. That was the attempt anyway. That 1 over 1 plus t squared anti-differentiates to tangent inverse of t. The middle component anti-differentiates to sine inverse of t, and then sine of t anti-differentiates to negative cosine of t. Oh yeah, plus a constant. So I didn't show the step that has the integral sign itself, but you can imagine here, right? So plus a constant. To find out exactly what that constant is, we should set t equal to 0 in what we have so far. And when you do so, you'll notice things are not quite the same as in the previous one. This first vector, the one that's in front of the plus sign, is not going to be the all zeros vector because of what cosine of 0 is, right? So be careful here. Arctan of 0 is 0. Arcsine of 0 is 0. But cosine of 0 is 1, and copy the minus sign. So you have a negative 1. All right, 0, 0, negative 1 plus the c vector that we don't know yet is equal to the 2, 3, 4 vector. Subtract the 0, 0, negative 1 vector on both sides, and you get that the c vector needs to be 2, 3, 5. Okay, so that means that the position vector is the general antiderivative we had, except we're now replacing the c vector that we didn't know at the time, now with 2, 3, 5, which we know, and then we can go ahead and simplify by adding the two vectors here component-wise. Okay, this really will constitute for us the end of chapter 13. Let's just take a moment to preview what's going on in chapter 14. So in Calc 1, a typical function looks like this. F of x equals 3 to the x plus sine of x. Something like that. The point is there's one real number as input, called x here, leading to one real number as output. In this case, 3 to the x plus sine of x. Right? So you feed in a number in as x, you get a number out according to the formula 3 to the x plus sine of x. In this chapter, in chapter 13, which we are just closing out, you have a vector function, like the one shown here, where the first component is 4 minus t squared, the next component is 1 over 1 plus t squared, and the third component is ln of 5 plus root 1 plus t to the fourth. And the point for these kinds of functions, these vector functions, is that you have one real number as input, and though the output is really just a vector each time, right? So you feed in a number and you get out a vector, one vector. The amount of information in the vector is three numbers, three real numbers, right? At least for 3D vectors, one vector is really three separate numbers. And now in chapter 14, we're going to switch, in a sense, the roles. In chapter 14, we're going to look at a new kind of function. Chapter 13 looked at a new kind of function, vector functions. Chapter 14 looks at a new kind of function. And in the new kind of function, just the notation I think will give it away. F of x comma y comma z is given by the formula x plus z squared times quantity x minus y cubed plus x to the eighth times y, for instance, as one example. This has three real numbers, x, y, and z, as input. So in order to apply this function, to use this function, you have to provide an input called x, an input called y, and an input called z. That's different from the type of functions that we've been looking at in chapter 13, where you just need to provide an input t, just a single number. T is 7, right? Now you would need to do, in chapter 14, say x is 8 and y is 9 and z is 10, for instance. And once you've fed in all three things, a number for x, a number for y, and a number for z, then this formula here would compute for you one real number as output, right? So you could... I know that in chapter 13, the technical way of saying it is the output was one vector for each input, but let's just speak in terms of how many real numbers occur. And so in Calc 1, it's one real in, one real out. In chapter 13, it was one real in and it was many reals out. And in chapter 14, it's going to be many reals in and only one real out.